This is the video of Introduction to Rational Functions, the warm-up. Use synthetic division or long division to divide. So I'm going to go use synthetic division here. So you make this bracket here. And then to the opposite of positive 3 would be negative 3. And then use the coefficients here, 1, 5, 11, and the constant term is 15. So bring down the 1. And multiply negative 3 times 1 is negative 3. Add, you get a 2. Multiply negative 3 times 2 is negative 6. Add, you get a 5. Negative 3 times 5 is negative 15. Add, you get a 0. So you get a remainder of 0 there. So x plus 3 is a factor. The answer you get here is x squared. So 1x squared plus 2x. So 1 less than the degree of the expression you started with, plus 5. And then in factored form would be x plus 3 times x squared plus 2x plus 5. If you wanted to find all the zeros, then you equate each factor to 0. X plus 3 equals 0, or x squared plus 2x plus 5 equals 0. X equal negative 3. And then plugging into the quadratic formula, you end up with x equal negative 1 plus or minus 2i. So here b is 2. The opposite of 2 is negative 2. B squared is 4. Minus 4 times a is 1. C is 5. And then 2 times a on the bottom. So 2 times 1 is 2. And then you simplify everything and end up with negative 1 plus or minus 2i. The objective, students will learn the key vocabulary associated with rational functions, including discontinuity, increasing, decreasing, vertical asymptote, horizontal asymptote, slant asymptote, and whole. The definition of a rational function, a function that is the ratio of two polynomials. It's rational because one is divided by the other like a ratio. Note the polynomial we divide by cannot be 0. An example would be x squared plus 5 over x plus 2. Today we'll be studying rational functions of the form f of x equal 1 over x and the transformations of this graph. So definitions, a horizontal asymptote is a horizontal line that tells how the function will behave at the very edges of a graph. The horizontal asymptote is not sacred ground, however. The function can touch and even cross over the asymptote. Vertical asymptotes are vertical lines which correspond to the zeros of the denominator of a rational function. They can also arise in other contexts, such as logarithms, but you will almost certainly first encounter asymptotes in the context of rational functions. The slant or oblique asymptote occurs when the polynomial in the numerator is 1 degree higher than the polynomial in the denominator. A function is increasing on an interval if for any x1 and x2 in the interval, then x1 is less than x2 implies that f of x1 is less than f of x2. A function is decreasing on the interval if for any x1 and x2 in the interval, then x1 is less than x2 implies that f of x1 is greater than f of x2. In other words, we read the graph from left to right. If the y values are increasing, then the function is increasing. If the y values are decreasing, then the function is decreasing. Discontinuous, there are breaks or jumps in the function. I have to lift my pencil to draw the function. a whole before putting the rational function in the lowest terms, factor in the numerator and denominator. If there's the same factor in the numerator and denominator, there's a whole. Set the factor equal to 0 and solve. The solution is the x value of the whole. To find the y value of the whole, you just plug into the x value into the simplified form, and you'd find the y value. So here's an example. This graph, f of x equal 1 over x. The horizontal asymptote is y equals 0. The vertical asymptote x equals 0. The function's always decreasing. The function's decreasing at, or let me say that again. The function is discontinuous at x equals 0. We call this infinite discontinuity here, where there's a vertical asymptote. Here's a graph, a practice graph, 1 over x plus 1 plus 2. The horizontal asymptote is this horizontal line right here, y equal 2. The vertical asymptote is x equal -1. Notice that we're adding 2 here. That's the horizontal asymptote. The vertical asymptote, -1 would make this denominator 0. So that's the vertical asymptote. Can't divide by 0. Is the graph increasing or decreasing? If I read this graph from left to right, then both branches are decreasing. The graph has infinite discontinuity at the vertical asymptote x equal -1. Practice 2, there's the function. What's the horizontal asymptote? It's right here at y equal 4. Notice we're adding 4 there. What's the vertical asymptote? X equal 3. That would make this denominator 3, and 3 would make this denominator 0. So vertical asymptote is x equal 3. Is the graph increasing or decreasing? As I go left to right, that graph is decreasing. Infinite discontinuity at the vertical asymptote x equal 3. Practice 3, -1 over x plus 2 plus 3. Horizontal asymptote, y equal 3. Or if I look at the graph, y equal 3. If I look at this, -2 makes the denominator 0. X equal -2. Look at the graph. That's where the discontinuity occurs at x equal -2. Is the graph increasing or decreasing? This one, as I go from left to right, the y values increase, so the graph is increasing and has infinite discontinuity at the vertical asymptote x equal -2. Practice 4, -1 over x minus 4 minus 2. Notice I'm subtracting 2 here. So y equal -2 is the horizontal asymptote, or if I look at the graph, I can see that here. What makes this denominator 0 is a 4. And that's my vertical asymptote, x equal 4. Is the graph increasing or decreasing? So left to right, this graph is increasing. And discontinuity at the asymptote x equal 4. How do we find the vertical asymptote of a rational function? We equate the denominator to 0 and solve for x. For example, f of x equal 1 over x as a vertical asymptote at x equals 0. When we equate the denominator to 0, we get x equals 0. We don't have to solve that one. Example 2, f of x equal 1 over x squared minus 4. Equate the denominator to 0. X squared minus 4 equals 0. Add 4 to both sides of the equation. X squared equals 4. Takes the square root. We have x equal plus or minus 2. The above function would have vertical asymptotes at x equal 2 and x equal -2. So we could prove that to ourselves by going to the Desmos calculator here. And the function was f of x equal 1 divided by x squared minus 4. And you can see that that does have vertical asymptotes at x equal -2 and x equal +2. How do we find a horizontal asymptote? On the previous slides, the function was written as f of x equal a over x minus h plus k. The function is, when the function is written in this form, x equal h is the vertical asymptote, whatever makes the denominator 0, and the horizontal asymptote is y equals k, what's ever added or subtracted here. When the function is the form f of x equal p of x over q of x, where p and q of x are polynomial functions, if the degree of the numerator is less than the degree of the denominator, then y equals 0 is the horizontal asymptote. If the degree of the numerator equals the degree of the denominator, then the horizontal asymptote is y equal leading coefficient of the numerator over the leading coefficient of the denominator. If the degree of the numerator is greater than the degree of the denominator, there's no horizontal asymptote. So here's some examples. So if I had 3 over x plus 2 minus 4 as a vertical asymptote, x equal -2, that makes this 0 on the denominator. Horizontal asymptote, 4 is subtracted here, so y equal -4. If it's written in this form, so once again, what makes the denominator 0, -2, and then the degree is 1 here and degree is 1 here, so equal the degrees, then you put the leading coefficient -4 over the leading coefficient 1, and you get y equal -4 over 1, which is -4. In fact, f of x and g of x are the same function written in different forms there. For f of x equal 1 over x has a horizontal asymptote y equals 0 because 1 has degree 0 and x has degree 1. And then this has degree 3 here, the numerator, and this is degree 1, so no horizontal asymptote. How do you find the slant or oblique asymptote? If p of x over q of x is equal to f of x, then the degree of the numerator is 1. And if the degree of the numerator is 1 greater than the degree of the denominator, then the slant asymptote is the quotient when you divide without the remainder. So if I divide x squared divided by x plus 1, the result is x minus 1 remainder 5. Therefore, the slant asymptote is just this, y equal x minus 1. The slant asymptote is not a testable item this quarter, but you will see slant asymptote again in pre-calculus and calculus. There'll be a slant asymptote problem in this activity to give you more practice with polynomial division. So use polynomial division to get the function in the form y equal a over x minus h plus k. So if I use the synthetic division here, put a -3 here, then a 4, and a 13, and you bring down the 4, then multiply -3 times 4 is -12. You add, you get the remainder 1. So this would be 4 plus 1 over the divisor, which is x plus 3. If I write this first, then you have f of x equal 1 over x plus 3 plus 4. So one way we could find the horizontal asymptote is the degree of both of these is 1. You do 4 over 1, therefore y equal 4 is the horizontal asymptote. Or we look up here, and we're adding 4. The vertical asymptote, x plus 3 equals 0, x equal negative 3 is the vertical asymptote. Same thing here. X plus 3 equals 0, x equal negative 3 is the vertical asymptote. And then on slide 15, you want to do the division. Here again, I'm going to use synthetic. Put a 5 here, a 2, and a negative 11. Bring down the 2. 5 times 2 is 10. And negative 1. So you get 2 minus 1 over the divisor here would be x minus 5. So if I write this with the negative 1 over x minus 5 first, then looks like this. F of x. Whoop. Get my fingers on the right keys here. Equals negative 1 divided by x minus 5. And then plus 2. Let me get in the equation under here, plus 2. The horizontal asymptote would be y equal to vertical asymptote x equal 5. So 5 makes this denominator 0 or over here. And then 2 over 1 is 2, or look right here, adding 2. Y equal 2 is the horizontal asymptote. And then 15, you want to do a negative 5, and then 6, and 29. Multiply, get negative 30 here. So this would be 6 minus 1 over x plus 5. And written in the form above here. Negative 1. Oh, I'm getting in the equation editor here. Negative 1 divided by x plus 5. And plus 6. Horizontal asymptote y equals 6. Asymptote x equal negative 5. So what's that makes the denominator 0, negative 5. This is added, so y equals 6. Or over here, 6 over 1 is 6. What makes the denominator 0, negative 5? So find the slant asymptote. And since this is pi r 1 and this leading coefficient is 1, we could use synthetic division again. So you get negative 1 here. 1, 3, 5. So bring down the 1. And then multiply -1. Get a 2, multiply. Get a remainder of 3. I can ignore the remainder. So y equal x plus 2. So it's just the quotient without the remainder. So the slant asymptote y equal x plus 2. And then find the whole. So first you're going to factor the numerator and the denominator. So the numerator factors into x minus 7 and x plus 2. Whoops. X minus 5 and x plus 2. Well, this should be x plus 2. And this should be x minus 5. And then factor the denominator. This factors into x plus 2. And x plus 1. Now I can take these parentheses away here. So we take the like factor here, x plus 2, equate it to 0. Because that's the like factor. And when I solve that, I get x equal -2. And then these cancel, so f of -2, you plug it into the simplified version of the function -2, wherever there's an x in the simplified form. So you get -2 minus 5. And then divided by, this should be a 2. And then -2 plus 1. Equals -7 divided by -1. And that equals 7. So the whole is at -2, 7. So let's go ahead and graph this and show you x squared minus 3x minus 10 and x squared plus 3x plus 2. And let's see what happens at negative 2, 7 when I put my mouse on that point there. Negative 2, 7 is right here. And notice it's at negative 2, it says it's undefined. So technically there's a hole here. The Desmos calculator doesn't plot that hole, but if you click on negative 2, 7, it says negative 2 and undefined. And if you look back at the original problem, if I put a negative 2 in here, it makes this denominator 0. So there's a hole in this graph at negative 2, 7.